Well, good morning, everyone, and I'll start. It's 8:02, and 38 of us are connected, which is not 93, which would be nice, but we'll go with this. And since it's recorded, latecomers or no-shows will be able to catch up as they watch our high-quality videos that's threatening the cat video on YouTube for the number of views. Just kidding. So the topic for today is more on probability and simulation. I think it has a formal name. We'll get to that shortly. And what I'm doing now is first a quick question that can be answered in the chat box. So what I should be sharing is a browser window, and the screen in front of you right now should have Zoom in it. Big old white screen with the blue letters Zoom. If that's correct, somebody tell me in the chat box. Yeah, yes it is. Okay, good. So we're good there. I'm going to make this a little bit smaller. Oh, good. It stays on top. Perfect. So that I can see the chat box as well as Farang. That way we can monitor it as I bore you to death for the next hour. So our lesson for today is not going to link because why? Oh, it hasn't detected a chance to obtain revenue in a few minutes. Okay, so in the class Blackboard, there is already a web link to our lesson, so I'm going to take that and execute the link. That looks like it's running correctly. So a quick description. This lesson introduces probability as the chance of occurrence of some event, and concepts of sampling and empirical distributions are introduced. I would say that second sentence is a bit of a lie as of right now, but probably in a few semesters that'll be true. The note links, we're going to take the lesson 11 link in a second. The original PowerPoint files developed by the team are in this lesson 11 link, original PowerPoint. I've moved the content of most of that into a Jupyter Lab notebook, which will allow me to bore you by doing presentation material, but still have the ability to run scripts live during the presentation. And then Laboratory 11, the link is active, so that is there. And when we get to Laboratory 11, Farang will take you through that and explain the nuances and interesting things. And then the reading, the only one that links is Computational Inferential Thinking, our textbook for the class, and there are cross links in the Jupyter Notebook to the relevant parts of computational and inferential thinking for this lesson. And recent updates don't mean much to y'all, but it looks like it reflected the recent ones. So very good. So we're going to go to lesson notes, and in lesson 11 we're going to want to I'm going to show you the HTML. This is how you can view what the notebook looks like. So this should be pretty cool, because any lesson that's got a great white shark on it's got to be good, right? And then now I'm going to go actually to the Jupyter Hub server, and I hope it's working. Oh, please. Give me the little spinny beach ball thing. As Hannibal says, he loves it when a plan comes together. So I love it when it actually works. Okay, so here's our notebook. Let me make a quick check to be sure that everybody is getting in the meeting. Okay. So to begin with, randomness and probabilities, we discussed that a little bit in our last meeting, but here we're going to carry it on a little further. And in this lesson, we want to introduce probability as the chance of the occurrence of some event. And these words are actually specific. They're kind of buried in these sentences to look sort of like folksy, talky, but they actually have precise meanings. And so an event in a probability context is a state or an outcome at some point in time. So the event could be my car turns blue after I paint it. It could be as convoluted as that, or as simple as the rock that John Muir is standing on falls finally from old age and failure. I think John Muir is going to fall from old age and failure a bit before the rock does, but nevertheless, that's what's an event. And then the chance of occurrence is the probability after a long time of observation that that event will have occurred. So there is a chance of occurrence that the sun that drives our solar system is going to burn itself out. Well, over an infinite period of time, that chance is probably a pretty assured thing unless the scientists are all wrong. But the chance of it happening tomorrow is pretty low. And we're also going to hit on the concepts of sampling and empirical distributions. You get more of that in the laboratory, and we're actually going to talk about it quite a bit precisely in the next lesson. So most of the content comes from the link here in our textbook in the Chapter 9, Randomness. And in that link, it has the following sentence related to probabilities. Over the centuries, there's been considerable philosophical debate about what probabilities are. Some people think that probabilities are relative frequencies. Others think they are long-run relative frequencies. Still others think that probabilities are a subjective measure of their own personal degree of uncertainty. And there's more to the paragraph that came from. Again, they're trying to be colloquial in explaining what probability is. As a practical matter, in engineering, science, and mathematics, and in the current state of affairs, election buying, probabilities are relative frequencies. There's a branch of statistics called Bayesian statistics, and they argue that there are no relative frequencies, but the fact is, Bayesian statistics are simply conditioned relative frequencies. So the concept of relative frequency is well established in the mathematics of probability, and that's what we mean by a probability. By convention, the values of probabilities themselves take on values between 0 and 1, continuous and inclusive. Or equivalently, we use the terms 0 and 100%, or various other ranges. The point is that probabilities are mapped onto, at some point, are mapped onto an interval between 0 and 1. By definition, impossible events have a probability of 0, and events that are absolutely certain have a probability of 1. And I have no mental concept of negative probability or probability that's even more sure than 1. So I went to school at UCLA a long time ago, and there was a, perhaps you've seen movies from like the 70s, and the certain probability events would be like for sure, and it's a terrible pun that I really can't share. But back in the 70s at UCLA, there was no such thing as a sure thing. So we never had probabilities get anywhere close to 1. But that was a different time and era. Let's consider an example of what's meant by essentially zero probability. So there's a photograph of a great white shark jumping out of the water, looking for something to bite. The probability that that great white shark can swim up the sewer, come up into your house, and bite you on the bottom while you're on the toilet is 0. It's not going to happen. You can worry about a lot of stuff, but that's not something you have to worry about. It can't happen for a couple of reasons. First is most sewer pipes, by the time they're at your house, are 3 or 4 inch inside diameter. That shark isn't going to be able to get up that small of a pipe. Secondly, especially here in Lubbock, we're a long way from open salt water. These are pelagic species, which means they live out at sea. So the shark physically can't get to us. It's impossible. The probability of a great white shark swimming up your sewer pipe and biting you in the bottom is 0. Now, if we change our situation a little bit, let's say we go swimming in a freshwater river. Let's say we're magically blessed by the gods of not freezing to death to have enough body fat that we can actually swim in the Columbia River, which is a bit on the cold side. And maybe we're 1 or 2 dams upstream from the coast. So that the probability of getting bit by a great white shark there might increase a tad. Maybe 1 in 1 million, 1 in 100 million, or 0.0000001% chance. And let's study if that chance, not the numerical value, but a non-zero chance makes any sense. Great white sharks are a pelagic species adapted to salt water. Okay, so I'm swimming in water. Great white sharks live in water. Possible. The water I'm swimming in is fresh water. Sharks live in salt water. So there's one plausibility disconnect right there. I'm up in one of the pools behind a dam, so the shark would have to get up a few fish ladders. Fish ladders are made for salmon, 3 feet long at the most, not 18 feet long like this guy here. And then if it gets up there in the wrong kind of water at the wrong temperature, is it still going to be hungry enough to bite me? And so if all those conditions occur, then yeah, it's possible. It'd be a very rare bite, but not physically impossible. Hence, if we were assigning probabilities, that situation all combining would be non-zero, but still small. I mean, it'd be essentially 0. I wouldn't bet your life on it. This next photograph is John Muir standing on a rock formation. This whole thing he's standing on is called Glacier Point. It's in Yosemite Valley, and there's not I couldn't find a super good photo of the whole arête or the nose at Glacier Point, but it's slightly overhung for several hundred, maybe approaching 1,000 feet. And then at the bottom, not in this picture, but at the bottom it starts to slope out to hold the rock up. So in terms of sure things, if you were to jump off that rock, it's almost guaranteed that you'll make that 1,000-foot plunge until you hit the apron of the cliff and make a big red smear. Now there could be a gust of wind that pushes you away into the trees, but that's pretty unlikely. So if you're not wearing your squirrel suit and you don't have a parachute, you're pretty much going to expire, 100% chance. That's what's meant by a sure thing. So the event of you performing an act of dumbness and jumping off this, and then the consequences that occur for that, the consequences that occur are the sure thing. Whether you jump off that is a matter of free will. Don't exercise it. And so that's an example of probability 1, and our great white shark biting us on the toilet is probability 0. So math is our main tool for finding probabilities, exactly in the cases where we can define populations and precisely define what are meant by events. Simulation, which we've already examined, is a good tool to provide approximations, and actually you get pretty close to absolute answers using simulation. So here we're going to look at some of the formal rules of probability, mostly to build in our tool set the ways to build simulations to do it in the future. I'll try to stick to the standard notation P of an event to denote the probability that an event happens, and then we use the words chance and probability interchangeably. So this notation's a little weird. So it's a capital P and then parentheses, like a functional form, and then what goes in the parentheses is the event, and the event can often be a word description. Later on in your probability and statistics class that you take outside of this class, completely independent of it, clever word choice there, the event might be the random variable x, usually expressed in lowercase, is greater than the value of x expressed in a capital case. The capital case is like the sentinel value, and then the lowercase x is what the random variable takes on. It's a notation that I don't think it's intentionally confusing, but sometimes you just have to slow down and read it carefully to understand what it's trying to convey. So let's look at a couple of situations. The first is what I call simple exclusion. Suppose that you have a definable event that either the event is precisely defined in such a way that the event occurs or it does not occur. Those are the only two possible outcomes. So the entire universe of outcomes is it happened or it didn't happen. If the probability that it happens is 40%, by the definition of probabilities, the probabilities must range between 0 and 1. If the entire remainder of the universe is the event doesn't happen, that has to be 60%. They have to add up to 1. And so that natural calculation can be described as the probability of not happening is 1 minus the probability of happening. And we're going to leverage that shortly. This result is only correct if the entirety of possibilities are enumerated. That is, the entire population is described. Happens and doesn't happen, as long as those describe all the possible states, then a simple exclusion is an appropriate tool. An extension of that is something called enumeration. And complete enumeration simply means that we're going to completely examine all the possible states that can occur and then assess the probability from there. So let's consider a die, which we've already played with last class, and I think you're going to play with it some more. And I looked ahead at the lab. I think you get to play with some 20-sided die, which is pretty cool. Assuming I understand the notation of D6 and D20, then 20-sided die. But let's stick with an ordinary 6-sided die. And if we wanted to determine the chance or the probability that when we roll that die, an even number will show up. Die has 6 faces. It returns numbers 1 through 6, integer. Of those numbers 1 through 6, the numbers 2, 4, and 6 are even numbers. Of the total number it can return is 1, 2, 3, 4, 5, 6. So there's 3 ways for the die to produce an even number out of 6 ways total for the die to produce any number. And so the ratio of those two gives us the probability that the die shows an even number. In that case, the ratio is 3 parts in 6 or 1 part in 2. So half the time, if we roll a die, we expect to get an even number. If we were to modify our question and ask how many times will a die produce a multiple of 3, we again look at the universe of possible outcomes. So it can produce a 1, 2, 3, 4, 5, or 6, and say, is 1 a multiple of 3? Like, not really. Mostly what they mean by multiple of 3, can you divide it by 3 and get a remainder of 0? So 1 divided by 3 has a remainder of 2. 2 divided by 3 has a remainder of 1. 3 divided by 3 has a remainder of 0. So 3 is a multiple of 3. 4 divided by 3 has a remainder 1. 5 divided by 3 has a remainder 1. And 6 divided by 3 has a remainder of 0. So 6 is a multiple of 3. So there's 2 possibilities that are multiples of 3. The numbers 3 and 6. Out of the 6 total possible outcomes that the die can show when we roll it. And so the probability that the die shows a multiple of 3 is the ratio of 2 over 6, or 1/3. 1/3 of the time we'll get a multiple. No, that's not right. 3 times 2. Yeah, 1/3 of the time a multiple of 3. So to generalize what these 2 examples are trying to illustrate, the probability that an event happens is equal to the number of outcomes that make the event happen or define a successful event over the total number of outcomes. That needs to be retypeset. I'm going to take advantage of that while I'm here. Fix this thing. Won't be perfect, but it's going to look better. There we go. And I'll have to go back and put the white spaces back in. So in general, probability of an event success is all the things that would define success over all possible outcomes. And in these examples, this is provided that all outcomes are equally likely. That's valid for these examples. But if outcomes have different individual likelihoods, the example can be adapted for that quite easily. As above, the examples presume that the entirety of possibilities are enumerated. In the case of the single die, there's 6 outcomes. These comprise the entire population of outcomes. And population is bold-faced for a reason. If we roll 2 die, there's 12 outcomes. 3 die, 18, and so on. That's assuming we're counting up the numbers on the die. So as we get more dies, we can increase the population of outcomes. Alternatively, we can roll the die multiple times. And in that case, if we do the multiple rolling, we have to do a little bit of manipulation to explain the population of outcomes. The population is important later on when we get to descriptive statistics. A lot of populations we're interested in engineering are somewhat large, and in many cases we can't perform experiments on the entire population, especially if they're destructive testing. So we take a subset of the population called a sample, and we apply some rules of probability to the sample, and then we make the extrapolation that the sample represents the population. And that's pretty much why a cat in Arkansas is going to successfully predict the outcome of the next presidential election. Because that cat produces the representative results. So moving on, a second thing to consider is what I call conditioning, in that we're examining 2 events that have to happen in order for us to have defined a successful outcome. So let's read through the example and go through it. Suppose you have a box that contains 3 goats, one red goat, one blue goat, and one green goat. Suppose you draw 2 goats at random without replacement. That is, you shuffle the 3 goats, draw one, shuffle the remaining 2, and draw another. What's the chance that you get the green goat first, followed by the red goat? That was in response to a chat comment that they missed the goats. So there's 6 possible pairs of goats by color. Red, blue, blue, red, red, green, green, red, blue, green, green, blue. All these are equally likely by the sampling scheme, but only one of them, green, red, makes what we define ahead of time as the event occurring. And so the success event is when we get a green goat, then a red goat. So we could examine the probability of that happening, again by simple enumeration in this case. Green-red is what we are interested in, and the probability of that occurring is equal to the ratio of green-red divided by all the possibles. So red-blue, blue-red, red-green, green-red, blue-green, green-blue. And that adds up to 1 over 6. But the other way of arriving at the answer is to think about the event occurring in 2 stages. First, we have to draw the green goat. That has a chance of happening of 1 in 3. And that means the green ticket is drawn first in about 1/3 of all repetitions of the experiment. But that doesn't complete our event. Among the 1/3 repetitions when green is indeed drawn first, then we have to get the red goat. And that happens about half the time. And that's because there's 2 goats left after we draw the green one. So the probability of green first, then red, is 1/2 of 1/3, which is 1/6. Usually such a calculation is written in the chronological order of the experiment. So first we do a green, that happens 1/3 of the time. And then once we've drawn a green, from the remaining 2, half the time we'll pull the red. And the product of those 2 individual stage probabilities is the total probability for the event, in this case 1/6. The factor 1/2 is called the conditioning, or the conditional chance that the red ticket appears second, given that the green ticket appeared first. And it gets the word conditional actually from the literary description of that sentence. The chance that the red ticket appears second, given the condition that the green ticket has already appeared, is what's called the conditional chance. So in general, we can extend that to something called a multiplication rule, where the probability that 2 events happen is equal to the probability of one event happening multiplied by the probability that the other event happens given the first one has appeared. So that's the conditional probability multiplication rule. So when there's 2 conditions, one event must happen as well as the other. The chance is a fraction of a fraction, which is smaller than either of the 2 component fractions. The more conditions that have to be satisfied, so the more things that have to go right, or in the case of space shuttles, the more things that have to go wrong, the less likely they'll all go wrong. So that this is a probabilistic argument for complexity. But that's not necessarily a good argument for complexity, because usually the more complex things are, they find better ways to break than we could have imagined ahead of time. A second approach to almost the same kind of situation is called partitioning. And that's when the sequence itself doesn't matter. So if we instead want to ask the question, what's the chance that one of the 2 goats is green and the other red? That case does not specify the order in which the colors must appear, so they can appear in either order. The way to handle this would be to partition the event so that it can happen in exactly one of its total different ways, and then we examine the probability of that of those different ways. So the natural partition of one green and one red is green, red, red, green. Each of those two outcomes have a chance of 1/6 based on the logic expressed above. So we can calculate the chance of one green and one red by adding up the chances of either happening. So the probability of one green and one red is equal to the probability of green, red plus the probability of red, green, which is 1/6 and 1/6, which becomes 2/6, which is 1/3. So there's a 1 in 3 chance of pulling a green goat and a red goat if we don't regard the order of the pulls. So that produces what's called the addition rule, and it's stated as the probability that an event happens is equal to the probability of the first way it can happen plus the probability of the second way it can happen. And that's provided that the event happens in only two ways. And we can extend this to multiple ways to achieve an outcome as long as each way is unique. So the first way and the second way can't be identical, because then we're double counting probabilities and we will estimate the wrong value. So an event can happen in one of two different ways. The chance it happens is a sum of chances, and hence bigger than the chance of either of the individual ways. The multiplication rule has a natural extension to more than two events, and we'll look at that below. And the addition rule also can extend to events that happen in more than two ways. If you want to learn more about this stuff, you can take this link and you get to go to MIT for a few minutes and look at their lecture. So I will leave that for you to do on your own. That was as of 2014. I'm surprised that I was able to find those lecture notes. But it is a more formal, it's an MIT style presentation. So if you don't understand it, you must not belong here version of what we just did. The last thing we want to look at, and at this point we'll start to work our way into some scripts, is the idea of at least one success. This is a type of exclusion or partition argument. And this one's very, very powerful because it actually allows us to do some meaningful things. We often work with random samples from populations. And a question that sometimes arises is about the likelihood that a particular individual in the population will be part of the sample. So to work out that chance, that individual is declared a success, and the problem is to find the chance that the sample contains a success. As an example, if we're picking people out of a line at a concert and we want to get the person that has spots, what's the chance of picking out a spotted person if we just pick people at random? Depends on if you've listened to much Pink Floyd and you know what I mean about spots. To see how such chances are calculated, let's start with a simpler context. Tossing a single coin 2 times. If you toss a coin twice, there's 4 possible outcomes. You can toss it the first time and it comes up heads. You can toss it the second time and you get heads again. That's what's called the HH outcome in this discussion. You can toss it first time, get heads, second time, get a tails, that's head, tails. First time, get a tails, second time, get a heads, tail, head. Lastly, toss it once, get tails, toss it a second time, get tails. So we've abbreviated heads to H and tails to T. So the chance of getting at least one head in any 2 tosses is 3 parts in 4. So there's 4 possible outcomes, and 3 of them produce a head. So another way to come up with this answer is to ask the question, what's the chance of not getting any heads? Because 1 minus that chance is the chance of getting at least 1 head. For not getting any heads, both tosses have to come up tails. So the probability of at least one head in two cases is equal to 1 minus the probability of both tails, which is 1 minus 1 part in 4, which is 3 parts in 4. We also can look at the probability that we get both tails is simply the multiplication rule applied to the tail outcome. So in each toss, the probability of a tail is 1/2, and if we want to obtain that in 2 tosses, the result will be 1/2 times 1/2, or 1/2 to the power 2. And in fact, it becomes 1/2 to the power of the number of tosses. So these two observations let us find the chance of at least one head in any given number of tosses. For instance, the probability of one head in 17 tosses is 1 minus the probability of 17 tails in a row, which is 1 minus 1 and 2 raised to the 17th power. So now we have a logic tool to find the chance that the face with 6 spots comes up at least once in a roll of a die. And we actually already know the answer. If we roll a dice once, the probability of getting a 6 is 1 in 6, which means that the probability of getting a not 6 has to be the remaining probability, 5 in 6. But we can look at it using the addition rule. So probability of not 6 is equal to the probability of a 1 plus the probability of a 2 plus the probability of a 3 plus the probability of a 4 plus the probability of a 5, which is 1 6 plus 1 6 plus 1 6 plus 1 6 plus 1 6, which equals, wait for it, drum roll, 5 6. Therefore, the probability of at least 1 6 in 2 rolls is 1 minus the probability that both rolls are not 6, or 1 minus 5 parts in 6 raised to the power 2. The probability of at least 6 in 17 rolls is 1 minus 5 6 raised to the power of 17. And we can play that for quite a few different rolls of the die. So let's go ahead and do a little bit of pandemonium here, and we will we'll look at that in script form. So here's a script. I am not the original author, but I'm going to go ahead and change one part. We will create a variable called how many rolls to take. And let's just start with one roll. We'll make it dumb. Actually, I think this starts counting at 0, so I think I need to make it 2. Okay. So let's go look at the script. First, we're going to import pandas as PD, because somehow someone a long time ago thought that was a good naming convention, and so all examples involving pandas are PDs. Although that does save us 4 letters of typing every time we use a pandemonium function. And we have a variable called how many rolls to take. So we're going to take a die, and we're going to throw it this many times minus 1. So when I put in a 2, I believe we'll get roll 0 and roll 1. Now we have an empty list to keep track of the number of rolls as a list. And we have an empty list called probabilities. And what we're going to do is for each of the probability lists, we're going to enter this formula, but we're going to change the value of roll count based on how many rolls we're at. So our classic for loop structure that we're used to, we will take the number of rolls list and we'll append to it the roll count. So it's going to start from 0, then go 1, 2, 3, and so on. And we're going to append to that the computed probability of 1 minus 5 6 raised to the roll count power. Then we're going to use that to define a dictionary named roles. The key in the dictionary, one of the keys is going to be the number of roles. The other key is going to be the probability of at least 6. And the number of roles key is going to correspond to the number of roles list. And the probability of at least 6 key is going to correspond to the probabilities. We'll then take that dictionary, convert it into a data frame named DF. And from that, we'll produce a scatter plot where the x-axis is the roll count and the y-axis is the probability of at least 6. And here you see a graph from an earlier run. But now by changing how many rolls to take 2, we shouldn't get that many dots. So let's go ahead and run it and see if I haven't broken it. And it's a very boring script with 2 rolls. So if we take 0 rolls, the probability of obtaining a 6, of obtaining at least at least 6 is 0. If you don't roll the dice, you can't get a 6. If we roll the die 1 time, the probability of getting at least 6 is a little less than 0.175, and we can go look at that in the data frame head. 1.667, that stinkingly sounds like 1/6. That makes sense. I don't like the name of these keys. Probability of at least 1/6. Yeah, there we go. So we'll make a slight change. Let's see if that makes our graphic more interpretable. There we go. I like that. So actually what I did there was very good instructionally. I did my arithmetic pretty much correctly, but my plot had confusing axis labels. And so it's our responsibility as the programmer to alleviate that as best we can. And so by a subtle change in the name of the plot, I now am plotting the probability of at least 1/6 in 0 rolls is 0. In 1 roll is 1 in 6. Let's see what happens if we take 2 rolls. So in 2 rolls, we're getting up to 30%, and we can't see the curvature yet. Let me make a quick change. Now I think I have it counting correctly. Let's check. 1 roll. There we go. Now I have the roll count. Let's roll the die 10 times. So in 10 rolls, we expect to get a 6. We expect after 10 rolls, we should see at least a 6, one of those rolls. And that somewhat is supported by our probability plot. And it says by 10 rolls, we would have expected to see a 6 in one of those rolls with 85% chance. If we go to 50 rolls, after roughly 25 of those 50 rolls, we're almost assured that we'll see a 6 in one of the rolls. This can't tell us which roll that's going to occur. If it had that capability, you all could write the script, put it onto your phone, go to Las Vegas, and in less than a night be set for life financially. That's assuming that Guido lets you out of the casino with all your body parts. If they find out, they'd get kind of upset. But they might actually give you a job working at the casino, so that's not all bad. So that's using simulation to play the game. And if we take a look at the just the head of the data frame, we see that roll 4, the probability of at least 1/6 is nearly 50%. We can use the describe tool also. It's going to do correct descriptive statistics that are hard to interpret for this particular problem context. Plus, if I don't press the syntax correctly. But the median chance of observing at least 1/6 in 50 rolls is 98%, which means that you have a 98% chance that you're going to see a 6 in 50 rolls and a 2% chance that you won't. The mean is 88%, so it's still pretty high. So if
is that Houston?
Yeah, we'll get to that in a minute.
My hometown.
Yeah, that's Houston.
Of course, they flood easily.
So let's apply this same. That's right. You are at MIT. Is that cool or what? At a fraction of the cost, and you didn't have to learn how to speak Bostonian and park your car in the yard and eat butter. So let's extend these ideas to insurance. So this is a very simple but fundamentally important way of calculating risk. And I've entitled this section, Why Should Anyone Buy Flood Insurance? So someday you guys will buy houses, maybe. And if you buy a house that's located anywhere near water, which is pretty much on the planet Earth, your mortgage company will make you buy flood insurance, and you'll scratch your head. I'm on the top of a mountain in a desert, and it hasn't rained here for 5,000 years. Why should I buy flood insurance? So this example might illustrate the importance of that. So let's suppose you have a house that's located in the 100-year annual recurrence interval regulatory floodplain. And so those are precisely defined creatures in flood regulations. They use words to help confuse the paying public, but they're actually precisely defined things. So the 100-year annual recurrence interval is a nomenclature that refers to a probability of something happening in any given year of 1%. The regulatory floodplain is the distance. We'll use this picture to illustrate that. That probability is stated, and then using computer models that are far more sophisticated than the ones we're using right here because they have color graphics, they determine the top width of that flooding river at the 1% probability, and then they declare anything between the top width as flooded, and that's called the regulatory floodplain. And in Houston, for instance, which this is a photograph of, a few years ago they actually changed their rules that they go to the 500-year, which is the 0.2% chance flood, so even more rare, but also more big. So if you're anywhere in this regulatory defined flooded region, you're usually required to buy flood insurance. And you're thinking, why do I want to pay $1,000 a year for something I won't use? If it's a 100-year event, and we just had the last 100-year 2 weeks ago, I got 99 years to go. Well, that's actually not the case. So continuing on with the story, let's say the community we're in had a good engineer who actually got the probability correct. In other words, actually was able to create the regulatory floodplain by modeling, and it's reasonably accurate to what's really going on. And so that the chance in any year of a total loss is 1 in 100, or 0.01 decimal. So let's think of total loss in flood insurance. So when you buy a house, 30-year loans are quite common. So you borrow money, you buy the house, then you have to pay the bank for the next 30 years of your life, which sounds like a lot, but that 30 years goes by amazingly quick. Now, banks being what they are, if you're 15 years into that loan and you still owe them $250,000 and your house is washed away by a flood, you think the bank's going to slap its hands together and go, oh, bummer, man, you got no place to live. Well, You paid for the loan in good faith all the way up until the house was gone, so you're free and clear. Go. It doesn't happen. You still are obligated to pay off that loan or immigrate to a country without an extradition treaty. So what you're concerned with as a homeowner is you want insurance coverage to replace that house in the event of that total loss, which is a 1 in 100 chance, at least during the 30-year loan. So what you're very concerned is what's the chance of no loss in any year, what's the chance of no loss in 30 years, and so on. Because after your loan's paid off, you don't care. You're going to sell the house to the first sucker that comes by, and then you're going to move to a South Pacific island with a nice beach and drink whatever you like. We're going to go with Mai Tais. That's always a good drink. Pineapple and rum and something else. So that's your plan. So you want to ask yourself, what's the chance during a 30-year loan when I owe somebody else money of not incurring a loss? We can just apply the multiplication rule to that setup because of the way I worded it. And we're asking the question, what's the probability of no loss? That's 0.99 to the 30th power. So that number is almost 1, and it's multiplied by itself 30 times. Seems like, well, it's going to stay almost 1, right? Well, let's simulate that and find out. So literally adapting our prior script, okay, I wanted to turn the chart off on purpose, so that was done intentionally. Our prior script, all I did is I literally copied that, pasted it here, and then I'm going to make some name changes and so on. So we have an entry, how many years, so that's how many years in a row from the start of the loan that we want to evaluate probability of loss. We'll have a list called the number of years, another list called the no loss probabilities, another list called the loss probabilities, and these two were selected. This is mostly laziness on my part because you wouldn't need both. You would simply need a way to do the 1 minus to recover the other, because these are supposed to be one's complements of each other. And then we start marching through our simulation. So we're going to fix this first. So we'll go into how many years, and we will count the years based on the sequence. So we'll have years 0, 1, 2, 3, 4, and so on. We'll compute the no loss probability, which is 1 minus 1 in 100 raised to the year count. And we'll compute the loss probability, which is 1 minus 1 in 100 raised to the year count. We'll create a dictionary that has 3 keys: years from start, probability of no loss, probability of loss. And each of those keys corresponds to the number of years, the no loss probabilities, and the loss probabilities. We'll convert that dictionary into a data frame, and then we'll do some plots. And so what I've decided to plot is I'm going to plot the years from the start of the loan, the probability of a loss. So this is the chance of us losing our house and still owing the bank money for a physical object that no longer exists, which is the perfect situation in banking, but it's not the perfect situation as a person who borrows money. You want to have the physical object that you're paying money for. Otherwise, it's like paying money for nothing. Kind of like, I was going to say kind of like taxis, but no point in getting too political in this course, too cynical. So I'm going to plot years from the start of the loan, probability of loss. But let's do it for just 1 year. Okay, so the probability of loss in 1 year is remarkably low. It's 10%. It's 1%. 2 years, it's gone up to somewhere around 2%. 5 years, 5%. 9 years, 8.5%. 20 years, so the time it takes to get a baby old enough to kick out of the house and have them go to work and make money, 17.5%. And now the disturbing one, the duration of a loan, 30 years. The probability of a loss is approaching 25%. So in a 30-year loan, using the 1 in 100 chance probability as the definition of a flood zone, you have a 1 in 4 chance over that 30-year period of incurring total loss. So that means you're flipping a coin 4 times, and one of those 4 times it comes up tails. Well, actually, one or more of those 4 times it comes up tails. That's not good odds if you owe a lot of money, and so that is an incentive to buy an insurance policy to pay off the house note. And the probability of loss actually climbs amazingly quickly after just a few years. So in the first year we're at our 1%, and it's working its way up. There's slight curvature that you can't see. Now let's say you bought the house, you have no intention of moving because you got a house in a prime part of the world where nothing bad happens, and you're going to have an 80-year lifespan. You buy your house in the 20s, so how long is, what's the probability of a loss in a 60-year period? Basically, your time of living in that house. You go long enough, and we're getting close to a 50% chance. So one time during that 60-year period, the probability of it having a total loss is 50%. I have a good friend in Italy, in his family apartment that they live in, grandma, grandpa, his mom and dad, him and his family. Their apartments, so in Italy an apartment is like a giant apartment complex that the whole family owns. It's not what we visualize. Theirs is 600 years old, give or take a few years. So if they were in a flood-prone region, which they are, but if they were down by the river, the chance of them incurring a loss at the 1% chance is almost assured in a 600-year period. So sometime in that 600 years, their apartment has flooded and had to be repaired. He has interesting stories from his grandparents. This is a tangent, so that's how you know it's real professoring. So I'm talking about stuff that's not on the test. During World War II, they gave sanctuary to a German soldier and a Allied soldier in different parts of the apartment. I mean, it's a big building. And I always asked him, his name is Mario, interestingly. He said, that seems kind of crazy. He says, no, you don't know the Italian mindset. If the Germans rolled into town, we would present the German soldier and be heroes. And when the Allies rolled into town, we'd present the Allied soldier and we'd be heroes. Point is that our house would still be standing long after the war is over. So there's that's kind of a cool attitude that his family adopted that has worked for them for 600 years. And the last thing I wanted to look at is, let's go ahead and explore our data frame. See, I just did a 600-year run. So I should be able to get location 30, which tells us that the 30-year period, our probability of loss is 0.26 or 26% chance. Better than 1 in 4 of incurring a flood. And that's a very simple application of these probability ideas that is arguably realistic and important. And these are the kind of considerations that the flood insurance program goes through to determine the rates to charge you. So let's suppose that a total loss is going to be $100,000. So there's a 26% chance in a 30-year period of having to pay out $100,000. And so you want to, your expected loss from a probability point of view is $26,000. So you want to collect enough insurance premiums to cover that expected loss and make a little profit. And that's pretty much how insurance companies work. So they sell these premiums that doesn't add to a total payout. They've got a huge bucket of money buried in the ground for when, in case they have to make a payout. And then they also have a whole bunch of lawyers with cats and dogs, which we saw in the previous slide, so that when they have to make a payout, the lawyers can go to the courts and say, we don't have to pay them money. We just sold them a policy and took their money. That's the business part. But eventually they pay it out. And that's how premiums are set. They're based on these probabilities over a predictable life of risk. So that concludes what I have for the lesson. And if there's any questions, well, actually, I'll answer some of the questions in the group chat. So this photograph is downtown Houston in 2001, shortly after Tropical Storm Allison. And when I lived in Houston at the time, my house, let me get located. That's a Pierce elevated, so that's I-10 going that way. My house was off to the right of this photo, probably a couple miles from where this image was taken. This is taken from a helicopter. This area here, where you see the water everywhere, is mostly a bayou. Memorial Drive is right here. It's underwater. There's a few houses in this picture that are completely underwater, but there's not that many houses right along the bayou. But what's more dramatic in the picture is one of these is Interstate 10, and coming here is Interstate 610. There's a portion of US 59 that's one of these that's underwater. It basically shut down transportation for several days. And through this part of Houston, it's estimated that there's $1 to $2 million an hour of commerce occurs. So every day that's $24 million of commerce that's flushed down a toilet. So they don't want roads to be closed very long. So this was Tropical Storm Allison, and then there's a comment that Harvey was worse in 2017, and I can't really address that either way. I wasn't there for Harvey. I was there for this one. Tucked safely away. Over here where the, see, those got to be the Moody Towers. So my office at the University of Houston was right here somewhere. And I saw this coming on the radar and pretty much left work early, went home, and our neighborhood's not far from here. Our house did not flood, but we're basically shut in the neighborhood for 3 days. You couldn't go anywhere. Cars don't float so good. So flooding's a real thing. In the case of the Houston area, it's a relatively low relief part of the earth, which someone here has is flat. And so it takes water longer than we are accustomed to drain out into the Gulf of Mexico. The land surface elevation where this photo is roughly, like right here where this house is, it's probably elevation 70. 60 miles away is the Gulf of Mexico at elevation 0. So you can do the slope calculation yourself and realize that the slope's not 0, but it's really quite shallow. And when the water piles up like that, it just takes a long time for it to drain out. And eventually it did drain out. And Houston rebuilt like it always does. They were able to make it better, faster, more traffic congested than ever before. So that is my pontification on that. And as a motivational tool, this probability stuff is very much important in disaster preparation, disaster relief. And then the main thing we're after is this, is whatever the probability of no loss or loss is. The economic consequences are actually remarkably easy to estimate. The product of those two is how much money you have to have set aside, not necessarily in a bank, how much gross domestic product your nation has to have available to be able to recover from a disaster. And most nations have parts of the government that are tasked with doing that, but like our government, most nations, parts of the government that do the disaster projections are completely ignored until after the disaster occurs, and then they fire the people that did it because you didn't tell me in time. So that's just a sad part of the way things are. So I am going to clear off my screen. I think we can take a 10-minute break. So I have 9:09. At 9:20, Farang will pick up and go through lab number 11 with us. So let me stop sharing and give him, how do I say it in Star Trek? I give you the comm.
Thank you. And if you have any questions that you want to ask me, I'll be here for the next 10 minutes, so go ahead.
All right. So shrink all that. There we go. And that capture keeps capturing. So is a D20 indeed a 20-sided die?
Exactly, yes.
Okay. I having to learn all your gamer jargon the hard way, sort of figure it from context.
Actually,
I guess I could have typed it into the internet. Oh, terminology.
This is a D20.
So there's both physical representations of it as well as computational is trivial.
Yes. In D&D, Dungeons and Dragons, you have plenty of different dice. You have D4, D6, D8, D10, D20, and in some cases even a D100. But D20 is actually a very common and useful tool in D&D. Yes, Walt, D12 too. Yes.